All right, so today we're going to look at inverses, and we're going to use your skills from yesterday with your composite functions for part of this. So a highlighter would probably be handy. I put a bunch of definitions up here that are going to make sense as I go through example 1. So bear with me until we get through that. So we're going to look at inverse relations today. This brings you all the way back to your first year of algebra. An inverse relation is where the x and the y coordinates are reversed. The original function, bless you. So you might have the ordered pairs, I don't know, 1, 3. Negative 4, 5. 2, negative 6. And the inverse of that would be, just switch the x and y's. 3, 1. Notice I'm not changing signs. 5, negative 4, negative 6, 2. It's all an inverse is. Simple. With order of pairs anyway. Obviously, it's a little bit more complicated. We can look at an original graph of a relation, and we can determine if that relation, every relation has an inverse. Not every inverse is a function. So we have the vertical line test for relations to determine if it's a function. If I move that vertical line through that graph, it should only touch it once if it's a function. If the graph touches it more than once at any point, it's not a function. Same thing for that horizontal line test, but this time I'm holding my line horizontally through a graph. And it's through the original functions graph, or the original relation graph. If my graph passes that horizontal line test, the inverse of that function, the switching of the x and the y, will be, the inverse of that relation will be a function. Every graph, every relation has an inverse. Not every inverse is a function, just says not every relation is a function. You can have a relation that's not a function, but its inverse is a function. You can have a relation that's a function, but its inverse is not a function. So, we'll get more into that in a minute. Then we have one-to-one. A function is one-to-one whenever it passes, the original function passes both the horizontal and that vertical line test. So it has to pass both of it. So one-to-one if the graph passes both the vertical and the horizontal line tests. Every x is paired with exactly one y, and every y is paired with exactly one x. It has to pass both to be one-to-one. So you can have a function. The original relation can be a function, but it may not be one-to-one with its inverse. Well, we can test that if it passes both horizontal and vertical line tests, just graphically. Then there's a difference between an inverse relation and an inverse function. As I said, an inverse does not necessarily mean that it's a function. And then this is the notation for inverse functions. F to the negative 1. F to the negative 1 does not mean that we're taking the reciprocal of the base. So it's not a negative exponent. It's just notation for the inverse. And I don't read that F to the negative 1. You'll hear me say it only until you get used to it. Then after that, you're going to hear me say just the inverse of F. So if you see a cursive letter with a negative 1, with that function notation, parentheses some letter, that's your inverse notation. All right, so let's look at example 1 to try to make clear these 4 definitions. So it's asking which of the graphs below are A, relations that are functions. So what test do I use to determine if a relation is a function? The vertical line test, right? So as I move my vertical line through graph A, is it a function? Yes, it only hits that graph once at any point, so A is a function. What about B? Right there, not a function. What about C? Nope. What about D? Yeah, it passes. So A and D are the only relations there that are functions. Then part B. Relations that have inverses that are functions. That's your horizontal line test. So this is your horizontal line test on the original function. So I'm going to run my horizontal line through each of the graphs. If I run my line horizontally through this graph, does it only touch the graph once at any point? It only touches it once, so it passes, right? So A passes. What about B? B passes, right? I don't see any place where it touches it twice horizontally, so B passes. What about C? Right there, you can just see those endpoints. Aren't they horizontal to each other? Doesn't work. What about D? Yeah, right up here. Whoops, right up here at the top. It doesn't pass through here, right? So only A and B, these are the only relations whose inverses are functions. What is the only graph that passed both the vertical and the horizontal line test? A. That is the only relation that is one-to-one with its inverse. So every one of them has an inverse. Only these two inverses are functions once the inverse is drawn. These are not the inverses. This is the only function whose inverse is one-to-one to it. And that just means it passed both the vertical line and the horizontal line. Meaning both the function, the original function, and the inverse are both functions. So write yourself a note because you're not going to remember that. Graph A is one-to-one because it passes both vertical and horizontal line tests. Does that help to make more sense of this? Graphically, I'm just looking at vertical and horizontal line tests to determine if the inverse of a graph is a function, every relation has an inverse, and if a graph is one-to-one, meaning that both the graph and its inverse are relations because they both pass that vertical and horizontal line test. Now we can also do it algebraically, which we'll get through here in a minute. So example 2, let's actually find the inverse graphically. We can find an inverse, graphically. I want to do it algebraically here. I have written out the steps. This is something that you did last year in your second year of algebra. So know those steps. Very first step, let f of x be y. So we're going to swap out this f of x. We're going to replace it with y. So just switch that out. Then because I'm finding an inverse, and the definition of an inverse is that the x and y switch places, we're going to switch places with the x and y here. So for every y I have, I'm going to replace it with an x. And for every x, I'm going to replace that with a y. So every y became an x and every x became a y. So that's almost our inverse, but step 3 is solve this new equation now for y. That can get kind of hairy. So in this particular example, I happen to have a fraction equaling a non-fraction. Hence, I turn that into a proportion across multiply and solve. So that's what I'm going to do. So I get 1 times y is y. And then I've got x equals x times y plus 1. What do I do now? Yeah, it looks like I have it solved for y, but I have a y on the other side, right? So I need to distribute because this y is in jail. The only way to break it out of jail is to distribute that x into those parentheses. So I get y equals xy plus x. To solve for y, I have to have all the terms that have y in it on one side by themselves. Every other term that doesn't have a y goes on the other side. So xy has a y, I want to move it to the left with the other y. So I'm going to subtract an xy. Xy and y are not like terms, so you can't really combine them. But if I were you, I would write the positive one first, y minus xy equals x. sense so far? No? Were you confused? This one here? So I turn this, if ever I have a fraction on one side and a single term on the other side, I'm going to put that single term over 1. This becomes a proportion. X is to 1 as y is to y plus 1. Can't I cross multiply and solve? That's what I did to get there. Did I leave anybody else in the dust? Because if you don't tell me, I don't know. Are we good to go? Okay. Now I have all the terms with y on one side by themselves. I need to get the y by itself. I can't combine those, they're not like terms. What can I do? What was that? I can't do anything with an x. I can factor out a y, can't I? Each of these has a y in common, so factor the y out in front of the parentheses, and we're going to divide each of these by y. I'm factoring it out. Y divided by y is 1. These y's here cancel, I'm left with a minus x. Now I can solve for y. Y is being multiplied by 1 minus x. What do? Divide by 1 minus x to both sides. So the 1 minus x is canceled on the left, and we have y equals x over 1 minus x, but we're not done. Very last step says let y be, and that's the inverse notation. The negative part of the 1 got sucked up into the f, but that's y to the negative 1x. So the last part is just replace y with the inverse notation for the function, and you got x over 1 minus x. Any questions on it? Okay. And all they wanted was the equation. Sometimes they'll call it a rule, find the rule, it's the same thing. All right, so let's flip it. So that's finding the inverse algebraically. Let's find the inverse graphically. So I put the inverse reflection principle on here only so that you could see why we're doing this graphically this way. The points A, B, and BA, by definition, those points are inverses of each other because the x and the y are switched. In the coordinate plane are symmetric, and this is the important part, are symmetric with respect to the line y equals x. When you find the inverse of a point, symmetric to that line y equals x means that those 2 points are equal distance from that line. So when something is symmetric to a particular line, that means that they are equal distance from that line. So the points A, B, and BA are reflections of each other across that line. So I have created 4 graphs. You probably won't need 4 graphs to graph the inverse of a relation. You don't need to know the original function to graph the inverse. You just need to be looking at ordered pairs or eyeballing it a little bit, because in Math Excel they're going to have you eyeball it. So sometimes it's easier to create little points for yourself and then reflect it on your paper yourself, and then compare that to your answer choices. So we should all be able to recognize that isn't this the graph of f of x equals x cubed? Right? And on this graph, I've put 3 specific points here. I've also put a point up here where the arrows are and down here that are slightly off the graph. So the first step, before we talk about the ordered pairs, first step you are to draw in the line y equals x. That's your line of reflection. That's where your eyeball should be focused on. So 0, 0, if you don't know how to graph this, just start plugging in points. If x is 0, y is 0. If x is 1, y is 1. Well, that's this point right here, 1, 1. If x is 2, y is 2. If x is 3, y is 3, and so forth. Same thing with the negatives. If x is negative 1, y is negative 1, negative 2, and so forth. And so that is your graph, y equals x. We're going to reflect that original over that. So some of you, because you're just naturally spatially gifted, you can do it without the ordered pairs help. You can just see it. The rest of us have no ability to do that. So draw that y equals x line here again on the second graph only, not the third one, or not the fourth one, just the second or third graphs. You're going to want to see that line as well. So in order to do this reflection, I'm going to look at ordered pairs. So if I look at ordered pairs to find the inverse, I can just switch the x and the y. So let's look at some ordered pairs that are on this original function here. I'm going to ignore 0, 0, just because. Let's just look at the first point, 1, 1. Isn't 1, 1 on the y equals x line? If something's on the line, how far is it from the line? 0 distance. So isn't the reflection point also 1, 1? When you switch 1 and 1, don't they look the same? So they are 0 distance from the line, just to let you know. So it doesn't look like they changed. But if I take 2 and plug it into x cubed and cube it, what do I get? 8, right? So this order pair way up here is 2, 8. It's just slightly off the graph. That's 2, 8. And then let's go on the negative side. So I've got negative 1 when cubed is negative 1. We have negative 1, negative 1. And then negative 2 cubed is what? Negative 2 cubed. Negative 8, isn't it? Negative 2 times negative 2 is positive 2 times negative 2, negative 8. So there's 4 points that are going to help me reflect. So our second step, we are going to plot the inverse point, BA. So we've got to create these inverse points. Yes, because that's what the original function is. This line right here that we're going to take the inverse of, it's y equals x cubed. So I knew that when I plugged in points, so if you happen to know what that is, you can get your ordered pairs by plugging into the original formula. If I don't know that that's what that is, then I'm just going to do my best to create the points that I see on there and try to reflect those. I'll create points that look like nice happy integer points. Okay? And so I found those points either looking at the graph or using that formula. And so now we're going to reverse those points. So 1, 1 still looks the same, right? Isn't it 1, 1? 2, 8 is now 8, 2. So let's just stop there. We're going to plot those 2 points. So 1, 1's already here because it's part of the original graph also. But 8, 2, we're going to go to the right 8, which means I have to go 2 off of my grid and then up 2. So here's that point 2, 8 right there. Connect 0, 0, 1, 1, and 8, 2. Doesn't it look like that? Visually, as you look at these, don't they look like as the graph is curving away from that y equals x line? Yes, it's getting further and further away from the line, but each successive point, so if this is 8, 2, and this is 2, 8 right here, aren't those 2 points equal distance from y equals x? And if I choose another point out here, 3, 27, and 27, 3, they're going to be equal distance but further from the y equals x. So each successive x, the y's get further and further away, but the inverse points are always the same distance from each other to that y equals x line. And if you were to fold this graph on that y equals line, wouldn't that fold over onto that green line? Visually it does. So let's look at the bottom half of it. So the bottom half, I'm going to reverse negative 1, negative 1, so that looks the same. Negative 1, negative 1. And I'm going to reverse negative 2, negative 8, and make that negative 8, negative 2. So I'm going to plot those 2 points. Negative 1, negative 1 is already plotted. But negative 8, go to the left 8, so you have to go slight root 2 off, and down 2. So there's that point there. Connect the 0, 0, negative 1, and negative 8, 2. And again, you see that same pattern happening here. Those are equal distance away. And if we were to fold the green onto the black, the green would lay onto the black at that y equals x line. So then our last step is to just show the graph. Of the inverse function of x. So I'm going to just draw these points again, but I'm not going to draw on the y equals x, and I'm not drawing on that original function. So I'm plotting 0, 0. I'm plotting 1, 1, 8, 2, because I want to look at it without everything else in there. I'm plotting negative 1, and negative 8, and negative 2. That's the inverse of this function here. Are they one-to-one to each other? Does the original function pass a vertical line test? Yes, and does it pass a horizontal line test? The fact that it passes a horizontal line test tells you the inverse is a function and isn't the inverse a function. And because it passes both, these are one-to-one to each other. Yes? This one here? Did you understand how I got my points? Okay. All I'm doing is plotting those points. All I did was take these points, which I got by reversing those, and all I did was plot them and connect the dots. That's all I did. And the reason why we redrew it out here was so that you could clear away all that other stuff that's there and just see what it is that I plotted those points, plus the 0, 0 point. But I wanted you to see that it is symmetrical, that y equals x line, and that each of these points are symmetrical to that. Now, there's lots of you that can go directly from here to here, and you won't have those in between, and that's fine. Once you see it, you're like, okay, I got it. And this is really a double reflection. Is really what it is. Okay, so, yes? Because remember the definition of one-to-one says that the original function passes a vertical line test and the horizontal line test. Because it passes both, essentially, because both are functions, that's why it's one-to-one. Both of them have to be functions. And as you look at the graphs, they're both functions, right? So they're one-to-one. All right, so then we're going to use the inverse composition rule to actually find a one-to-one inverse function. You can determine, if I give you a function and its inverse, you can tell if it's one-to-one. Well, you can tell if it's an inverse by doing the following. We're going to use fog and goth. If I use fog for the function and its inverse, or what we think is the inverse, and I get x, I have to do it also for goth. If they both come out to be x, simplify to x, then I have a function and its inverse. You ready? Let's do number 4. So let's just do what we did yesterday. Let's do fog. F of g of x equals. Same thing that we did yesterday. F is my outside function, so I'm going to take the f function, which is right here. That's my umbrella function. I'm going to use parentheses wherever I see, oh, that's a cube, wherever I see an x, I'm going to use parentheses. Then I'm going to input g of x into wherever there was an x. So in this case, wherever there's a parentheses. So I'm going to input the cube root of x minus 1. Are we okay with that? What happens when we cube a cube root? Don't you get what's left underneath that root? And then don't forget the plus 1 that was outside. So the negative 1 and the positive 1, don't they cancel? Aren't we left with x? So it simplifies. F of g of x, fog, simplifies to x. So far, so good. Can't stop there. You have to also find goth, g of x, g of f of x. So g of f of x equals. So g is on the outside, so we're going to use g as the umbrella function. So I'm going to rewrite g, but everywhere there's an x, I'm going to put parentheses. There's my umbrella function. Inside those parentheses, I'm putting in f of x, which is x cubed plus 1. So we're okay with that. Alright, so then underneath that cube root, I can drop those parentheses. And don't the constants 1 and negative 1 cancel out? And you're left with the cube root of x cubed. What does that equal? What does that equal? It's x. So g of f of x is also equal to x. So what the inverse composite rule says is that, oh, well, they are inverses of each other. And it's 1 to 1. So they are the same. Well, they're not the same. They're both x's. So both, and I'm going to abbreviate here, composite functions equal x. So they are inverses of each other. And let's just see quickly, if I have time, to prove to you that they're also, let's look at the original function. Isn't that a cubic function? This is no different than this graph right here, correct? Wasn't this graph both, wasn't this graph 1 to 1? Pass both the vertical and horizontal line test. All this does is move it up 1. So I'm not going to graph that. Both of these are, they're inverses of each other and they are 1 to 1. Did I not put that on here? Inverses of each other and 1 to 1. All right, so the last question, you got to write small. It's going to have some domain restrictions on it. That's the part that you have questions on. So we have to show that the function has an inverse and find the rule for it. So we are going to find the inverse doing what we did on example 2. So step 1, what do I do first to find the inverse? Swap out f of x, right? For y equals the square root of x plus 3. Now what do I do? Step 2. Now what do you do? Switch the x and y. So I get x equals the square root of y plus 3. Now what do I do? Solve for y. So how am I going to solve for y? You've got to square both sides because y is underneath the radical. So whatever that radical is, in this case a square root, that means I'm squaring both sides to break that radical out of there. And so I get x squared on the left, and I get just what's underneath that radical on the right. Now this one's pretty simple to solve for y, isn't it? Don't I just subtract 3 from both sides? Are you okay with that if I use a symmetric property at the same time and get y on the left side? Well, I'm going to. So I have y equals x squared minus 3. But I'm not done, because the final step, I have to swap out that y for its inverse notation. F to the negative 1 of x is equal to x squared minus 3. Now, if you were to graph x squared minus 3, that graph, that's the inverse of the original graph, and it is a function, but it's not going to end up being 1 to 1 until we restrict it. So watch what happens, because it doesn't pass that the horizontal line test, does it? So when they ask for the domain of f and the inverse function, start here. Doesn't this affect the domain? It's a radical. So wouldn't we take the x plus 3 and set it greater than or equal to 0 for the restriction? So we've got where x, if I solve this, I get x is greater than or equal to negative 3. Agreed? And y, what kind of answers do you get for square roots? You get positives and 0. True? So y is going to be greater than or equal to 0 because y is the answer to a square root. When we switch the x and the y here, you switch the x and the y here. So we get where y is greater than or equal to -3 and x is greater than 0, greater than or equal to 0. And then that gets brought down to here. So what's going to happen, this function is going to get restricted to only the part where x is greater than or equal to 0. It's only going to look like this. From -3 down here on up. And your domain, written in interval notation, would look like this. Your domain is greater than or equal to 0. So bracket 0, positive infinity. And your range starts at -3 and includes it and goes to positive infinity. If we don't restrict it, it won't be 1 to 1.
What's the y greater than 0?
Because on this one, because the answer to a square root can only be positive or 0, because we're going to take the square root of 0. It's not going to come out negative, because when I ask you what's the square root of 4, you're going to tell me 2, not -2. Does that make sense? Because if we want to restrict this and make it 1 to 1, we have to take original restrictions, which you'll agree that that's restricted original, isn't it? So we have to take those original restrictions and we have to reverse those restrictions like we reverse the x and the y. That affects your final answer, the restrictions. They're not going to ask you that on every question, but they are going to ask you that on the exam. So you take into account your original restrictions, switch them. And all I do is switch my x and my y, and they should become your other restrictions. So this equation right here has another half to it. Okay? But for them to be 1 to 1, to switch back and forth from the inverse of a function to be 1 to 1 and to be an actual function, if I left that inverse as a parabola, it passes a vertical line test, but it doesn't pass the horizontal test. Whereas on this one, no matter which way I do it, that passes horizontal and vertical, that passes horizontal and vertical no matter what. I don't have to restrict this. But on this one, the inverse would have another half to that. I have to restrict that if I want it to be 1 to 1.
So how could you have it on the left side and on the right side?
Because when we switch the x and the y, those switched. Because if you look at this, now y cannot be greater than or equal to -3 because that's restricted because of the radical. And the x is only going to have an answer that's positive or 0. Because this is your inverse right here. Because we switch the x and the y. Up here?
Yeah.
Because your answer to that y is coming from the square root. Square roots only have an answer that's 0 or positive. If I ask you to take the square root of 4, you're not going to tell me -2. You're going to tell me 2. Does that make sense? So that's why I know that the answer, the outcome of any square root is going to be a positive answer or 0. It's going to be the outcome. Because the domain was restricted, my outcome is restricted. And if you think of the square root function that goes like this, well, from your perspective, this way, that's the graph. It's only got positive y values on that graph.
Oh.
Right? Okay. Anything else? No, I am not. Yeah, that was